Okay, so I want to move into the second law of thermodynamics. As you'll see, and we cover a little bit later, the second law of thermodynamics, unlike the first law, it does have a definition, but it's better described through multiple definitions and examples. So I will be posting a video also to kind of just help your understanding of the different aspects of the second law of thermodynamics. But I just want to go through and let's go ahead and just start writing down. Oh, let me turn this around. Okay, so I want to go through and talk about some aspects. Let's see. Aspects of the second law of thermodynamics. Okay, and so we know that from the first law, the conservation of mass and energy, that mass and energy cannot be created or destroyed. And for a process, conservation of mass and energy principles indicate the deposition of mass and energy, but do not infer whether the process can actually occur. And this is where the second law comes in. So the second law of thermodynamics provides the guiding principle for whether a process can occur. So let's go ahead and write that. So second law provides the guiding principle for whether a process can occur. So I'm just going to restate that. So the conservation of mass and energy principles, mass and energy cannot be created or destroyed, right? So you just spent an entire class learning about that, putting that into practice, things like that. And then for a process, conservation of mass and energy principles indicate the deposition of mass and energy, but do not infer whether the process can actually occur, right? So that's where the second law comes in. It provides the guiding principle for whether a process can occur. So the second law of thermodynamics have a ton of aspects, and the ones that differ from the conservation of mass and energy are that they are predicting the direction of a process. This has been referred to by some as the most important part of the second law of thermodynamics. It establishes conditions for equilibrium, which you'll see in problems that we work, determines, I'm frozen a little bit. Okay. Okay. Determines the best theoretical, oh my gosh. Okay. Sorry, guys. Theoretical performance of cycles, engines, and other devices. Okay, so this, just this little section determines the best theoretical performance of cycles, engine, and other devices. This comes into play when, say, someone is manufacturing a new type of engine or a new type of device, rather than just build it and then measure it and watch it and research it in use. You can use the second law to help determine the best theoretical performance and make changes before you go into the prototype or the manufacturing phase. Then it evaluates quantitatively the factors that preclude attainment of the best theoretical performance level. Okay, so just kind of piggybacking on this determines the best theoretical performance. We can then evaluate it quantitatively. And here's some other aspects. Let's see. Defines a temperature scale. Independent of the properties of any thermometric substance. And then also very important, it develops a means for evaluating properties such as U and H. And it's, let's see if I can make this, yeah, U and H in terms of properties that are more readily obtained experimentally. Okay, and then just a little excerpt. Scientists and engineers have found additional uses of the second law and deductions from it. It also has been used in philosophy, economics, and other disciplines far removed from engineering thermodynamics. So that's just a little excerpt that I found in some notes that I thought was really interesting. We know that thermodynamics is not exclusive to mechanical engineering, but it is kind of nice to see. You don't think of it being used in philosophy or economics. I think I'm going to post a TED Talk that is an example of that. It was really interesting to me. So before we move into the second law of thermodynamics statements that we will use to actually help define the second law, I just want to go through and mark out some differences between the first law and the second law. So first law and second law. Or really, some of these are the same. So just important aspects of it. So this establishes, the first law establishes a property called energy, and we evaluated that extensively. And this establishes a property called entropy. So remember, we had these in the tables and we used this in the first law equations, but we didn't really delve into what entropy was. We just quantified it. So this will vastly help you understand what entropy is, which is a very difficult for some concept to understand. Okay, and so these two. And then here we've got energy can be stored and transferred. Right, that was the whole first law right there. And then entropy can also be stored and transferred. Then here, energy can be conserved, or really energy is conserved. Okay, and it cannot be created. It cannot be destroyed. Again, it's the whole first law. But here, entropy is not conserved. It can be created. And in some ways, it's always being created. And it cannot be destroyed. So I want to pause here and take a moment to talk about entropy. So entropy is not conserved, okay? It can be created. It cannot be destroyed. So if you have entropy here, right, on an XY, right? And let's say this is entropy right here, and this is time. So if we have entropy over a certain amount of time, and it starts here, if it can't be destroyed, but it can be created, it's either going to just stay here based on just these two, or go up, or anything in between. But right here, it says energy is not conserved. So because of that, it's only ever going to increase. Entropy is only ever going to increase. So that's these three notes in a visual aspect, right? Okay, so entropy is never conserved, so it's not going to stay the same. It can be created, which means it can go up because we can create entropy, and it cannot be destroyed, so it can't go down. So it's only ever going to, look like this, or look like this, or look like that, or, somewhere in between here. Okay. And then, let's see. For the first law, you cannot extract more energy than the total energy present in the system. So that makes sense. Energy is conserved. It cannot be created or destroyed. So therefore, there's no way that you can extract more energy than the total energy present in the system, because then that would mean that you would have needed to create more energy. And then for the second law, you cannot extract more work from a system than the available energy present in the system. So we know this also because we know that we move energy by way of work or heat transfer, right? Q or W. So if we only have a certain amount of available energy, we can't turn that into more work than what our energy can do in a system. So those are common sense. And then let's talk about the difference between available energy and total energy. Let's make that a little bit nicer. Okay. Okay, so just some notes. Available energy is the amount of energy that is accessible to convert to work. So that's what we define as our available energy, whatever is available to convert to work, whatever we can use. Okay, when a temperature difference exists between two bodies, heat naturally flows, you guys know this law, from a higher temperature to a lower temperature. Okay, and then the amount, so that just lets you know the direction. The amount of thermal energy available for conversion to work is based on the difference in temperature between parts of the system. Okay, so let's read that a little bit slower. The amount of thermal energy available for conversion to work is based on the difference in temperature between two parts of the system. So I want you to think of our cup example here. So if we've got a hot cup and a cold cup, and when we put those together, we're going to have heat flowing from the hotter cup to the colder cup in the end goal of thermal equilibrium. Well, to make those transfers, we have to have energy. Our energy is being moved between those two cups by way of heat transfer, by way of Q. So if we get to thermal equilibrium, there is no energy to move. They're both at the same, there is no transfers there. So the amount of thermal energy available for conversion to work is based on the difference in temperature between parts of the system. If you have two cups that are only 10 degrees difference, instead of two cups that have a 50-degree difference, there's going to be more available thermal energy for conversion in the 50-degree difference than there is the 10-degree difference. Okay, and then the last is unavailable energy equals total energy minus available energy. I know that's a no-brainer, but it is important to note. And why it's important to note the unavailable energy is because the unavailable energy is our entropy. So right here is where we can define, loosely define, I mean, it is entropy, but I know it's going to take a lot more for everyone to really understand what entropy is, but it's the measure of the unavailable or unavailability. Did I spell that right? Yeah, I did. Okay. Of energy, i.e., measure of how much of the system energy cannot be converted into work. Okay, so it's the measure of the unavailability of energy. So whatever our available energy is, the remainder is our unavailable energy, also known as our entropy. Okay, so now that we've discussed some of the differences, let's go ahead and start talking about just the second law. So the second law, there's, like I said before, there's really no simple statement that captures all of the aspects of the second law. I briefly mentioned that, a couple of people, or I say a couple, a group of scientists believe that the best thing that came out of the second law is the direction of time or the direction of a process. And then some people say, well, actually the best thing to come out of it was entropy and the measure of disorder and things like that in the universe. There's tons of different aspects of the second law. So there's no real nice, neat way to define it. But we do kind of lean on two statements to help with that. Second law, alternative statements. Okay. And so these are, well, there's actually three. There's the Clausius statement, and then there is the Kelvin-Planck statement, and then the entropy statement. And something interesting about these two in particular is that while they sound very different and we lean on them for different things, they are actually saying the same thing. So let's talk about those really quick. So, Clausius statement of the second law. Okay, and so what this statement says is it says it is impossible for any system to operate in such a way that the sole resultant, actually really it's sole result. Well, what is happening? There it is. Okay, sole result would be an energy transfer by heat from a cooler to a hotter body. Okay, so why is this important? Well, we know that heat naturally flows from hot to cold. If you have a hot glass of tea on your table, the heat is going to move from the tea into the atmosphere. The cooler atmosphere is not going to come into the tea and cool it down, right? So what Clausius is saying is he's saying that it's impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. So let's think about, first let's find a system that actually does transfer from cooler to a hotter body. And we can think of, everyone's got one, a refrigerator, right? So we keep our refrigerator cold. We keep it cold, 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 cold. We put something hot in there and it cools down the food, right? So you could look at this and say, well, but we all have refrigerators, or an AC, that's another one. But what he is saying is that it is impossible for any system to operate in such a way that the sole result, that's the difference, the sole result would be an energy transfer by heat from a cooler to a hotter body. So what do we need for both that AC and refrigerator to run? Well, we need electricity. So we know that 100% of the work going into that refrigerator is not going to just be from cooler to a hotter. We need an external force coming in to move that train there, right? Because what happens when you unplug the refrigerator or unplug your AC? It stops cooling. So it is not the sole result. It's not just going to naturally and magically go from cold to hot. So that's what it says when it says the sole result. There are so many other actions and energy transfers that need to happen for an AC or a refrigerator to work. You can't just build a refrigerator or an AC and leave it and it's going to naturally perform in this way. So that's what he's saying. And to just draw a little schematic, let's see. Okay, so say you have these two, this one's hot, this one's cold, okay, and say you have a metal bar between the two, okay, which is this and this. And so if you have a heat transfer going from the hot to the cold, that's good. Yes, we can do this. This is great. But right here, we have a heat transfer going from cold to hot. We cannot do this. No. That's what it's saying. Okay, that's all that the Clausius statement is doing, is saying that, hey, it's never going to on its own just go from a colder to a hotter. So this in that direction of a process, this helps you understand what direction a process can change. So that's what some people say is one of the most important things coming out of the second law. Okay, and then to get into the Kelvin-Planck statement, we're going to need to know a thermal reservoir. So let's go ahead and define that first. Okay, and a thermal reservoir is a system that always remains at constant temperature, even though energy is added or removed by heat transfer. Okay, so let's read that again. Thermal reservoir is a system that always remains at constant temperature even though energy is added or removed by heat transfer. So we can approximate these by looking at examples such as Earth's atmosphere. That's a good one. What's another one? Lakes and oceans. Pretty much has a constant temperature. And then maybe a large block of a solid, like copper. Okay, so now that we've defined a thermal reservoir, let's look at the Kelvin-Planck statement. Okay. Okay, and then this statement is, whoops. Okay, I want to get this right. So it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy. Oh no, it's frozen. Oh no. Okay. By heat transfer from a single, this is the important part, single, oh no. Okay. Thermal reservoir. This is a long one. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. So let's draw a schematic so that you can kind of see how this is going. So we've got another thermal reservoir. Okay. And then let's just see. Okay. Right here. And just put a cycle on here. Okay. And then this is what we're looking at. Okay, so let's denote our system. Okay, and so what it's saying is, well, let's note what this is. This is the system undergoing a thermodynamic cycle. Okay, and so what it's saying is it's saying that if we have heat from a single reservoir, so this is heat transfer cycle, and then we have work from the cycle, that this cannot happen. Because we cannot have, it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. So this is not possible. Okay, let's get back and pick up a new page. Okay, let's go ahead and see what we can define for entropy. So we've got entropy statement of the second law, which is my personal favorite edition of the second law, is the defining and use of entropy. So Mass and energy are familiar examples of extensive properties used in thermodynamics, and entropy is another important extensive property. Let's do extensive property. And what do we know about extensive? We know that it is dependent on, that's weird, dependent on the size of the device or whatever we're measuring. Okay, so entropy is another important extensive property. How entropy is evaluated and applied, we are going to detail in chapter 6, but we're just going to introduce it here. So unlike mass and energy, which are conserved, entropy is produced within systems whenever non-idealities, such as friction, are present. So while we are introducing entropy here, it will be more heavily covered in chapter 6. But unlike mass and energy, which are conserved, and we learned that with the first law, entropy is produced within systems whenever non-idealities such as friction are present. So we need to note that. See. Unlike mass and energy, which are conserved, entropy is produced. So remember that comparison chart that we just did 20 minutes ago or so ago that said that entropy is produced, never conserved or decreased. Entropy is produced within systems whenever non-idealities such as friction are present. Okay? And this is the entropy statement. Okay, and we're going to cover this more in chapter 6. We're just introducing it here. So the entropy statement is, it is impossible for any system to operate in a way that entropy is destroyed. Okay, so again, if the entropy statement is it is impossible for any system to operate in a way that entropy is destroyed, then it's never going to reduce. And if we don't conserve entropy, then the most likely or default answer is that entropy is always going to increase with our direction of time. So let's look at irreversibles and kind of how those idealized situations work into theoretical performance that we mentioned before. So we have, how close am I? Okay. So we have irreversibilities. And one of the important uses of the second law of thermodynamics and engineering is to determine the best theoretical performance of systems. So we kind of highlighted this a little bit earlier. Just think about from if you were running a company, how big of a deal in money and time savings this would be to be able to quantify and measure and compare theoretical performance of systems, whether it be existing systems or changes to systems or new systems. I mean, this would be huge. So the second law being able to further give this to when we say that it includes things like entropy or it helps establish the direction of time for a process. These things have directly affected the ability to look at, quantify, and measure theoretical performance of systems, which we've kind of been doing a little bit in the first thermodynamics class when we were quantifying things like flow and open systems and closed systems just in regard to the first law. But now that we're looking at the second law, we're able to put more aspects of this system into play and take into more consideration. And then also that direction of time and that direction of the process to really kind of look at the whole system and the entire process and see start to finish kind of what it's going to look like and be able to compare those two. One of the important uses of second law is determining the best theoretical performance of systems. Okay? And so then again, just like we just said, by comparing actual performance with the best theoretical performance, insights can often be had about the potential for improved performance. So we just talked about, hey, what about a change in a system? Well, which would you rather do? Look at it from a theoretical standpoint and say, hey, I'm about 93% positive that this is going to be a good change and it's going to save us time and money and resources and blah, blah, blah. Or would you say, hey, why don't we just implement this $2 billion change and then we'll measure it and we'll see if we should keep it? Or what if it's a change that you can implement but you can't come back from? So just huge value in the second law in implementing this. So by comparing, I think a lot of people implement aspects of this in their daily work and in their professions without even really considering that it's the second law of thermodynamics. It's probably because it's not neat and pretty and tied up in a nice little bow, but overall getting the same thing done by a lot of the same ways. Actual performance with best theoretical performance. Insights can be had about the potential for improved performance. Okay? And then best theoretical performance is evaluated in terms of idealized processes. So of course, an idealized process it's the best that you can imagine, right? So it's going to be for sure better than any sort of actual performance or process. So it's when we are firing on all cylinders, everything is running exactly as best case scenarios we can plan. So that's what we base our theoretical performance on. So best theoretical performance is evaluated in terms of idealized processes. Okay, and what does all of this have to do with irreversibilities? Okay, so actual processes are distinguishable from such idealized processes by the presence of non-idealities called irreversibilities. Okay, so let's note this and then kind of go into deeper detail on that. What are some irreversibilities that we encounter in engineering practice? Irreversibilities commonly encountered. A lot of these concepts are better explained through examples, or at least better grasped. So we have heat transfer through a finite temp difference. Okay. Unrestrained expansion of a gas or liquid to a lower pressure. Spontaneous chemical reaction. Spontaneous mixing of matter at different compositions or states. And then this was kind of mentioned above, friction and its sliding friction, as well as friction in the flow of fluids. Okay, so again, actual processes are distinguished from such idealized processes by the presence of non-idealities or idealities called irreversibilities. So the way that I kind of like to remember this is that it's almost that you just can't account for everything. I mean, we try to, but these are going to be things that are going to pop up and make our idealized process a real world process, right? So spontaneous chemical reaction. It's a spontaneous chemical reaction. Or friction. We get friction anytime two things touch, pretty much. So a flow of fluid or some kind of sliding friction. Heat transfer through a finite temp difference, right? So maybe even a temp difference that the device that you're using to measure is not even that precise enough to tell the difference in. And so then we're getting some of that heat transfer. So that's just some examples to kind of help you understand that. And then here's a few more just in different situations. So we've got electric current, flow through a resistance or polarization with inelastic deformation. Okay, and so all actual processes involve effects such as these listed, including naturally occurring processes, ones that involve devices we construct from the simplest mechanisms to the largest industrial plants. So just some examples to kind of help you wrap your head around what it means by the difference between a non-idealized process and non-idealities. And all actual, this is important, processes are irreversible. Sorry. Okay. Huge thing. All actual processes, actual, real world, actual processes are irreversible. All of them. Okay? And then a process that is reversible is when no irreversibilities are present. Woo! What happened here? Are present within the system and its surroundings. And the really important note for this is this type of process is fully idealized. So not real, pretty much. Okay, so we've learned a lot about irreversible and reversible, and I even have another little note to put in about this. But just before we get there, I want to give you guys an example of how to really understand what is a reversible process or an irreversible process. So a reversible process, a process is reversible if you can do something or if something happens and then you can undo it without any trace on the system or its surroundings, okay? So when I say that, I want you to think of a bucket with baseballs in it. And say you're walking with this bucket of baseballs and you trip and you spill the baseballs. And so that's your thing that happened. That's the thing that happened to the baseballs. And so you run around, pick them up, you put them back in the bucket, and you have undone that, right? So first you spilled it, and now you have undone it. You've picked them all back up and put them back in the bucket. And you think, well, I reversed it. I reversed spilling them. But that is not accurate. So what you actually did is two different things. You spilled them and then you picked them up, because a reversible process means that there is no effect in any way on either the system that you're looking at, like the balls or the bucket of balls, or its surrounding, which would be you. And so for you to clean up those balls, you had to exert energy, which meant that you had to put more food in your body, which meant that the plants had to grow more. So it's kind of a never-ending rabbit hole, right? And so also, in addition to that, the balls spilled. So we had potential energy that went to kinetic energy. And then back when you picked up the ball and you dropped it in the bucket, more potential energy that went into kinetic energy. So when you look at it that way, when I'm talking about a process is reversible, that's when we start talking about this type of process is fully idealized, because you can see how this is never attainable. Even if you had a cup of coffee and you put creamer in it and you mixed the creamer in, and then it just spontaneously unmixed, you would still have an effect on the surroundings and on the system. So this is obviously just not obtainable. So that's why we say all actual processes are irreversible. So that's how we know that all real world processes are reversible. And whenever we look at a reversible process, we know that we're only looking at that from an idealized point of view. So there is one that we consider to be internally reversible. So let's talk about that. Okay. So we do have one. We have an internally reversible process. And even then, it's not 100%. It's kind of like when we have an isolated system and we start calling things isolated system, but we really know that it's not 100% isolated, or when we're saying something is 100% efficient, but we know that it's not 100% efficient. This is one of these things also. So it's internally reversible, but we know that on 100% level, it's not 100% reversible. But it's internally reversible when no irreversibilities are present within the system. And irreversibilities may be present within the surrounding. However, okay, because we know that we're not going to get everything to be reversible. So we're looking at internally reversible when we're talking about quasi-static or quasi-equilibrium. So if you're not sure what that is, or you're not sure how this is playing into it, if you have something that's quasi-static, your trajectory kind of looks like that. We'll just say it looks like that. And so from a macro level, this is what it looks like. But when you look at it from a microscopic level, you pull out this portion right here. Okay, this is actually looking like this. Okay. And so what it's doing is in quasi-static, it's always trying to, let me see, it's always trying to reach a state of equilibrium. It's like trying to make up for itself. So you have something that goes up, and then to counteract that going up, it goes down. And then to counteract going down, it goes up. And then to counteract, and so on 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 and so on. And so then overall, this is a really, really small, slow speed that you would have to look at to view this quasi-static relationship that it has. And so when you break it out in a normal view, it ends up looking like this. So that's why we say we can have an internally reversible situation that is quasi-static, because it's on such a small and slow scale that these differences are trying to equal out, that it's trying to reverse itself, undo itself. It's just such a small amount. Okay, so let's just run through an example to help you kind of see how this would maybe be portrayed, especially in regard to internally versus externally irreversible or reversible. So water contained within a piston cylinder evaporates from saturated liquid to saturated vapor at 100 degrees Celsius. As the water evaporates, it passes through a sequence of equilibrium states. While there is heat transfer to the water from hot gases at 500 degrees Celsius. Okay, so this clues you in. It passes through a sequence of equilibrium states. Well, that's just what we talked about, that quasi-equilibrium, a sequence of equilibrium states. So for that, for a system enclosing the water, there are no internal oh my gosh, I need to erase that. No internal irreversibilities, right? Because we said it passes through a sequence of equilibrium states as the water evaporates. So as this is evaporating, it's passing through a sequence of equilibrium states. So for a system enclosing the water, there are no internal irreversibilities, because again, we concluded that a reversible process, internally reversible, is that quasi-equilibrium process. However, such spontaneous heat transfer is an irreversibility. Talking and writing these longer words, I get ahead of myself in its surroundings. And this is an external irreversibility. So while we can look at it on a microscopic level and kind of say, well, we don't have a fully reversible process, but if we break it down between internal or external, maybe we can have an internally reversible process and the external is irreversible. And so that's kind of what's being done here. And that's why when we say, hey, there's no process that is fully reversible, so that you can see that even when we break it down really on a microscopic level, that fully reversible process is just not there. Okay, let's leave this here, and we will pick up with applications and analytical forms of the Kelvin-Planck statement. We'll get into the Carnot cycles, things like that. So see you next lecture.